Welcome to MEI Mechanics. We're on the topic of dimensional analysis, and this is video 1.1, Dimensions of Quantities and Units. Now what you'll find in mechanics is that any quantity that we can use can be expressed in terms of the following three fundamental dimensions of mass, length and time. And it's important not to mix up the idea of dimensions with the idea of units. They are closely related. So when we think about units, we might be using units of kilograms, meters and seconds. And then other types of quantity like force, for example, or velocity, they will have units which are, or at least can be expressed in terms of the units of mass, length and time. And so the way that those units relate to each other for a given quantity will be the same as the way that the dimensions relate to each other. So you can work out one from the other, but in this video we're just talking about the dimensions rather than the units. So to start with, we're going to consider the dimensions of two quantities, velocity and acceleration. When we place square brackets around one of these things, that is indicating that we want to know the dimensions of that thing. So we know that velocity, units are meters per second, and that can help, or the fact that it's calculated as a displacement divided by a time. So that's a length, and then divided by a time, so L t to the minus 1. And acceleration, well, that is velocity again, but then divided by time. So another divide by time gives us t to the minus 2. Some other ones here: density, force, pressure, energy. Now depending on your experience of physics, you may or may not know how to write all of these things, but I would certainly advise you at this point to pause the video and have a go at this, and we'll talk about each one individually in a moment. Okay, so starting with density, so that's a mass per unit volume, so that must be mass, and then to divide by a volume, well, clearly volume is length cubed, isn't it? So that will be L to the minus 3, so we're dividing by a volume. Force, now this is an interesting one because we think of force as being newtons, but if we think about a formula involving force, we've got F equals ma. Just put that in brackets there. Right, that can help us to work this out. So it's a mass times an acceleration, and we know that acceleration is a length and then the time to the minus 2. Okay, so that has dimensions of mass times the dimensions of acceleration, which is at L and then t to the minus 2. So what that means is, of course, that as well as the Newton, we could say that the SI unit of force is a kilogram meter per second squared. It's a perfectly valid way of expressing the Newton. Now pressure, that is a force divided by an area. Alright, so if we write that down to start with to help us, so P is F over A, where A is an area. So that means I need to take the units of force, which are m, L, t to the minus 2, and then I'm dividing that by an area, which is L squared. So simplifying that, that's m, L to the minus 1, t to the minus 2. And finally, energy. Well, we know that is Newton meters. That's one way of thinking about it. Another way would be thinking about it as a half mv squared. It doesn't matter, as long as you can use any valid formula for any type of energy, and you will find it reduces to the same dimensions. So if we think about it as a force times a distance, for example, then I can take the dimensions of force, which is mlt to the minus 2, multiply that by dimensions of distance, which is another L, so that tells us that the dimensions of energy are m L squared t to the minus 2. We're now going to consider the dimensions of an angle. Now this needs a bit of careful thought. Certainly when we're working in radians, we know that there's a relationship between the angle and the radius of a sector and the arc length associated with that sector, which is simply that this s, this arc length, is r theta, or in other words, this angle theta is s over r. Okay, so that's length divided by a length. So that presents us with a difficulty, clearly, because what we conclude from this is that angle doesn't have any dimensions, and so we refer to this as a dimensionless quantity. Okay, so we'll just say it's dimensionless. And that was when we're working in radians. Even if we're working in degrees, for example, it's just a case of converting between radians and degrees. We're multiplying by pi over 180 or dividing by pi over 180, depending on which direction we want to convert in. Those are both just numbers, and pure numbers have no dimensions either. So any measure of angle is dimensionless. Okay, so another one that we're going to consider now is frequency. Now that comes about when we're counting something happening which is happening repeatedly, and so it could be cycles of a wave, for example, so the number of times that the peak of a wave passes in 1 second. Again, the thing that we're counting with frequency is something that's just associated with a number. It doesn't have a dimension. So it's a dimensionless quantity, but we're counting that, how many times that happens over a certain amount of time. So we end up dividing by a time. So that means that frequency has dimensions of t to the minus 1. Angular speed, sometimes called angular velocity as well, that's radians per second. Well, remember, radians are dimensionless, so the only thing that's going to give this a dimension is this per second, so dividing by a time. So just like frequency, angular speed or angular velocity or angular frequency is still t to the minus 1. Now sometimes it's useful to work out the dimensions of a quantity which appears in a formula like this. So this formula is associated with extensions of springs. We're told here that the t here is a force, x is an extension, which is a length, the length by which a spring's been extended, and L is the natural length of the spring. So if I'm interested in the dimensions of lambda, it's going to be sensible to begin with to rearrange this as lambda equals t L over x. And then when we think about the dimensions, so the dimensions of lambda, well, dimensions of t, now be careful here, t isn't a time, t is a force. And the dimensions of force, if we remember from earlier, were m L t to the minus 2. And then we've multiplied by a length and divided by a length. So in the end that just cancels down to m L t to the minus 2. So in fact this constant lambda has the same dimensions as force. So that concludes video 1.1, dimensions of quantities and units. The next video will be 1.2, dimensional consistency.